Alright everyone, welcome to the second video in the MathBytes series on vectors. In the last video, we introduced the idea of the vector and talked about some properties of vectors, as well as how we can represent vectors graphically. In that video, we also looked at some examples of how we can use these graphical representations of vectors to quickly compare different vectors visually. In this video, we'll be diving into how to actually add and subtract these vectors graphically. Because there are so many physical quantities that have to be represented by vectors, we'll need to know how to combine them and compare them so that later on in our physics curriculum, we can understand what happens when we have things like multiple forces acting on the same object, or want to know how to compare the momentum of one object to another object. Before we move on to discussing vector addition and subtraction, I want to let you know that this is one of those videos where it can be helpful to have a pen and paper, just so you can follow along with some of the simple exercises we're going to do. Remember from the last video that the displacement vector tells us about the difference between two positions. We had two dots A and B, and defined the displacement vector xab as the vector that points from A to B. Let's put another position on this page called position C, just so we can construct a second vector, xbc, to play around with. Like I said before, we're going to focus on learning the main ways of manipulating and combining vectors graphically. So the first thing we're going to talk about is how to add two vectors. Displacements are really nice to think about because we can directly interpret addition as following sequential directions. In other words, if I wanted to add vector xab and vector xbc together, you can interpret that in plain English as just let's go from A to B and then B to C. Graphically, when you add two vectors, you want to line them up so that the end of the first vector lines up with the start of the second vector. Some textbooks or lecturers or teachers or professors or what have you will call this adding vectors tip to tail. I kind of don't like this mnemonic just because I'm too lazy to remember which is the tip and which is the tail, but your mileage of course may vary. In any case, the result of adding two vectors together is a new third vector called the resultant vector. And the resultant vector is defined as the combined starting point and ending points of the two vectors we just lined up. In this case, the starting point is here at A, right? And if I follow this little chain of vectors sequentially, I'm going to end up here at C. And so the result of the directions A to B and B to C is really then just a vector that points from A to C. This makes sense because our change in position by walking along these two vectors is exactly the difference between positions A and C. In other words, if we followed these, we start at A and we end up at C, and our change in position is just the difference between those two positions. We can also add more than two vectors at a time just by tacking on more vectors to the end in the same way, making sure to line up the end of each vector with the beginning of the next vector. Also, interestingly, it doesn't actually matter what order you add these vectors up in. The resultant vector of a sum is always the same no matter what order I tack the vectors on. For the math nerds out there, this is called commutativity. We're not going to verify this here, but what you can do is just draw like 3 or 4 vectors, add them up in different orders, and see what the end result of adding those vectors up is. You should find that the resultant vector of those additions is always going to be the same no matter what order you put those vectors in. Okay, that's really all I have for vector addition, and so let's move on to the next operation, called scalar multiplication. So just like the way that multiplying two numbers is really just repeated addition, in other words, 2 times 3 is just what you get if you add 2 to itself, 3 times total, right? Scalar multiplication of a vector is really just repeated addition. For example, let's take xab and multiply it by 2. This new vector, which we can notate as 2xab, is secretly just adding two xab vectors together, in other words, vector xab plus vector xab. We can draw out those two vectors and actually perform this addition, and we find that the result looks like xab, but the length of this vector is twice as long, right? And so because scalar multiplication always adds the same vector to itself multiple times, the resultant vector of this operation is always going to give you a new vector that always has the same direction as the vector you started with, but it's going to have a different length. This gives us a really nice way to shortcut scalar multiplication graphically. I can just resize the vector to be longer or shorter based on the scalar I'm multiplied by. So for example, 3xab is the same direction as xab, but it's 3 times as long, whereas 1/2 xab is the same direction as xab, but it's just half as long. And so that's really all we need to know for scalar multiplication. All scalar multiplication does is really resizes the length of the vector while preserving the direction. And finally, the last thing we're going to go over in this video is vector subtraction. Vector subtraction is a little bit goofier to think about, and so what we're going to do is pick a silly example to work with so that we can kind of intuit the answer, and then we'll understand how to actually do vector subtraction afterwards. So here's our kind of warm-up exercise. What do you expect the result of vector xab minus vector xab should be? Take a second to think about it. If we follow the intuition we have for regular scalar subtraction, we expect this to be 0, right? Since it's a vector minus itself. It turns out that's the exact right answer. Just like in scalar subtraction, where subtraction is identical to adding a negative, we can construct vector subtraction in the same way. Vector xab minus vector xab is really the same as vector xab plus negative vector xab. And so that way we can rewrite subtraction as really just addition under the hood. But we run into this problem of having this pesky negative vector. And so when we're interpreting a negative sign in front of a vector, it's really just a scalar multiplication problem, but we're multiplying the vector xab by -1 here. In scalar multiplication, putting a negative sign has the effect of graphically flipping the direction of the vector it's applied to. In this case, that means that if xab is this vector, then negative xab is the exact same vector, but the start and the end are flipped around. In other words, negative xab is just xab, but I flip the arrow backwards. This way, we can now add vector xab to negative vector xab, and if I just follow these directions sequentially, I end up back at the place I started. Because we haven't changed positions at all, we should expect that our total displacement is just 0. So let's apply this idea of treating vector subtraction as really adding a negative and do a different problem. How would you compute something like xab minus xbc here? Take a second to work it out on your sheet of paper. Okay, let's go over the method for finding this resultant vector. So we're going to start by drawing vector xab, and we need to figure out what vector negative xbc is, right? Since what we're really doing is xab plus negative xbc. To do that, we can start by drawing xbc, and then recognizing that the negative sign has the effect of keeping the length the same, but just flipping the direction. We can draw our new vector, negative xbc, like so. Now we finish the subtraction problem by taking vector xab and vector adding the negative xbc vector to it. And our resultant vector goes from our initial position to the final position at the end of this little vector chain, right here. And so we have the resultant vector like so. It's important to note that while vector addition is commutative, vector subtraction is not commutative. This is also true for scalar subtraction, right? Like if you do 3 minus 5, that's not the same thing as 5 minus 3. Generally speaking, vector A minus vector B is not the same as vector B minus vector A. All right, that's really all I have for vector subtraction as well. And so, as per usual, before I let you all go, let's summarize what we've learned in this video. So in this MathByte, we learned that physics problems will often demand that we combine vector quantities, and we use the example of displacements to understand 3 key vector operations. First, vector addition, or in other words, stuff that looks like vector A plus vector B. Secondly, scalar multiplication, or in other words, stuff that looks like n times vector A, where n is a scalar value. And vector subtraction, stuff that looks like vector A minus vector B. Vector addition is performed by putting vectors in sequence from start to finish, and the resultant vector points from our initial point to our total final endpoint. Scalar multiplication is performed by just rescaling the length of the vector. In the case that you have a negative number in front, then the negative sign also has the effect of flipping the direction of the original vector. And finally, vector subtraction is really just vector addition and scalar multiplication combined under the hood. You can start by multiplying the second vector by -1, in other words, just flipping the second vector in the expression, and then adding it to the first vector. And so that's really most of the vector stuff you'll need for the first few weeks of intro physics. Later on, we'll run into some special vector operations called the dot product or scalar product, which is unfortunately not the same thing as scalar multiplication, and the vector cross product. But those don't happen until later in the curriculum, so we'll cover those in a different video. I hope this video helped you understand how to use the graphical representations of vectors to add, scalar multiply, and subtract vectors. If you have any thoughts or questions, as usual, please feel free to leave those in the comment section below. If you want some more practice, check out the office hours video on vector addition, subtraction, and multiplication, where we'll do a few practice problems with the graphical representations of vectors. In the next couple of videos, we'll jump into an algebraic treatment of vectors, where we'll learn how to represent and manipulate them algebraically so that we can do pen and paper calculations in like real physics problems. And finally, please don't forget to like and subscribe for more free physics problem solving tips. This has been Physics Tutoring Quantized.